Great. So I'm really excited to be here today to tell everybody a little bit more about modern time series analysis with a fairly new package in the data science space called STUMPY. For those of you who want to follow me on Twitter, you can find me at Sean My Law. As well, if you want to follow the development of STUMPY, you can also follow us at Stumpy_dev. So,
Sean, before, do you mind just hitting that button to hide that?
Yes, absolutely.
Sorry for interrupting.
No problem. Here we go.
Awesome, thank you.
Cool. So just as a reminder, we'll have a couple of pausing points throughout the talk. So be sure to ask your questions in the chat, and then I'll have Ollie relay them to me. So just so I don't forget to acknowledge the folks that really matter here that have done a lot of this work. So I want to acknowledge two research groups, one over at the University of California, Riverside, the PI there, Iman Keo, as well as at the University of New Mexico, Abdullah Muin. These are really the researchers that have produced and published a lot of these papers that are related to what you're about to see today. And Stumpy really basically just takes a lot of those ideas and sort of packages it into a very easy to use, user-friendly Python package. Also, obviously, I'd like to thank Ollie, Chippy, for inviting me to here to give a talk. As well, I'd like to thank TD Ameritrade, my employer, for giving me this chance to share this work with you. For those of you who aren't really familiar with TD Ameritrade, we're a financial trading firm. So whether you're a long-term investor, like a retail investor, or you're an options trader where you're trading futures, foreign exchanges, or just day trading, or maybe you're a financial advisor, we really offer a large amount of sort of fantastic platforms for investing, as well as great educational content. A few months ago, TD Ameritrade was actually made it onto the Fortune 500s list. So we're very, very proud of that. Now, as a company, our company purpose is to transform lives and investing for the better. And really the emphasis starts with transforming lives. One of the ways, as Ollie mentioned, that we are helping to affect our community here in Ann Arbor is I'm one of the co-organizers of PiData Arbor, along with Ben Zeitlin from NVIDIA, as well as Rose Putler from Duo Security. We've been doing this for a few years now. Check out all of our videos on YouTube. As well, a call for action here is the PiData sort of parent group is organizing a PiData Global with all of the local chapters across the world. And the call for proposals ends on August 2nd, so make sure you participate and submit a proposal for a talk. Just a little bit about me. I work on a team called the Exploration Lab as a senior research scientist and data scientist. And so on the Exploration Lab, our goal is to explore new and emerging technologies or methodologies that might help the company differentiate itself from our competitors. And Stumpy is one of these technologies that was first incubated in this group. So whether you're a data scientist, an academic, or maybe you're just like you're a analyst or a researcher, or maybe you're a software developer, engineer, or maybe you're managing a data science team, or perhaps similar to some of the people who are on this meetup right now, you're just a curious learner. Hopefully there will be something here for you. This talk is broken up into two parts. The first part is really to cover sort of the background and all the motivation. And then the second part, we'll get into live demos and a little bit of a review. So here's the problem. So we're talking about time series today. Here's the core of the problem. I'm sure everybody's been there before, where either you have some business team or a technology team, or maybe you're just collecting data, and this large amount of data lands on your lap. So in this particular case, somebody says, "Hey, here's some data. Now perform some magic, Dr. McFancy Pants. You've got a math degree or an advanced degree. Show me something interesting." And maybe you're lucky and you have a small data set where there's 10 data points, and you can visualize it very nicely and maybe pull out some quick insights from that. Maybe your data has 100 data points. It gets a little bit more complicated, but visualization is still possible. What if your data points get to about 1,000 data points? Now visual comparison of these data points becomes excessively hard. And then if you get to about 10,000 data points, forget about visualizing it, right? You really need to apply different analytics techniques in order to start analyzing this data. And once we get to things that are even beyond 10,000 data points, we've all sort of been there. We get this overwhelming, sense of dread. And you could just think that you wish that you had a magic wand where you can just wave it and maybe wish it all away. Or at least maybe you could wave some other magic wand that could at least tell you where you should focus your attention, right, when looking at your time series. And what are some of the classic ways that people might analyze their time series data? We talked about visualization, but obviously once it gets a little bit larger, it's impossible to use. You might reach for our good friends, stats, right? Where you might analyze, let's say, the mean or the median or some other global statistics like the max or the min. But very rarely when you're analyzing time series data, do you actually care about these sort of single point statistics, right? What you really care about are maybe a subsequence or a context of continuous parts of your time series and being able to extract meaningful information from that. Some folks might apply something called an ARIMA model, where you're basically building an autoregressive model. But this also assumes that you know that there's sort of a repeating pattern in your data, but not all data necessarily has repeating patterns. Or you might do some sort of anomaly detection, finding points along your time series that might be anomalous. Now, the problem with anomaly detection is that you first have to define what an anomaly is before you can detect it. Now, anomaly you might define as maybe a single point. But what if you see that point a second time? Is it still anomalous, or is it now normal, so to speak? So that's really a fuzzy gray area. And of course, we had two wonderful talks just right before this about time series forecasting. So leveraging tools such as Facebook Profit is a great idea. But this also assumes that you have either enough data or that you trust your historical data to give you reasonably good predictions of the future. And of course, everybody's favorite thing to do is, why don't we just throw more data at the problem, right? Or if you're really trusting every data, you might think about clustering these time series. But this really gets into an area where it becomes computationally expensive. And there's something that's very, very popular called dynamic time warping, where you take different time series and you stretch and compress those time series and see if they are similar to each other. And then last but not least, in the age of artificial intelligence, deep learning, everybody's favorite hammer looking for a nail to hit, right? But regardless of which method you choose to analyze your time series data, there's sort of one key point here, right? Which is that there's no silver bullet. Each time you choose a particular analysis method, you're looking at some sort of trade-off, obviously. And maybe just for the record, right? While I've studied time series for a good part of my life, I'm by no means an expert. Even still today, I'm learning tons from other folks. But really, what is the goal? So let's think about this. Let's simplify this a little bit. What is the goal of time series analysis? And to sort of answer this question, let's take a simple illustrative example. So here's a very, very simple time series that has 13 data points in it. So n is equal to 13. Now, as we mentioned before, we can maybe visualize it and look for maybe identify interesting points. But really, we want to look at maybe parts of the time series that may be repeating itself, let's say. Now, how might we analyze this time series? Now, to answer this question, being sort of a reformed scientist, so to speak, I like to pose this question to everybody who's on this presentation right now. So who is this person that you're staring at right now? Any guesses? Well, actually, you might know this person as William of Ockham. And he's actually best known for something called the law of parsimony. Or in modern science, we just simply call this Occam's razor. And Occam's razor states that simpler solutions are more likely to be correct than complex ones. So let's think about that for a second. Simpler solutions are more likely to be correct than complex ones. And so thinking more about what do we really want to do when we're analyzing our time series, we really should be answering this question, right? Which is, what is the most simple and intuitive approach that we can take in order to analyze our data? So how do we strip away that complexity? And hopefully some of the sort of key qualities of this approach might mean that the approach is easy to interpret. So it doesn't require you to perform tons of mental gymnastics in order to understand it. You should be able to look at it and interpret the results fairly quickly. Another quality is applying minimal assumptions. a lot of the times with the different methods that you're seeing today, especially in, let's say, machine learning or even in statistics, right? It requires some level of assumptions. Can we strip away as many of the assumptions as possible in the approach that we're trying to take? Also, it would be great if the approach could be parameter-free. Going back to the machine learning examples, right? And thinking about hyperparameter tuning or thinking about deep learning models where there's oftentimes millions, if not billions of parameters to fit. If we can simply, use an approach that maybe has no parameters or as close to that as possible, that would be fantastic. And then another great quality is to not have any prior knowledge, right? Because maybe it's a new data set, we don't know anything about it, or maybe we don't have time to train a machine learning model. So if we can leverage an approach that doesn't require any prior knowledge, then this sort of satisfies the constraints of having something that's simple and intuitive, right, and easy to interpret, and that isn't a black box. So going back to our illustrative example, maybe we should start with a definition. So we know that this is our time series. I like to start with a subsequence. So whenever you hear me say the word subsequence, all this means is that I'm referring to a part or section of the full time series. So I'm not referring to the entire time series, just a small part of it. So here's what I mean. So this is our full time series. This green rectangle over here denotes 2 points, and this can be a subsequence of length 2. Similarly, this is another subsequence of length 3, and your subsequence could be as long as, let's say, of length 8. So all of these are considered subsequences. So now that we understand what subsequence means, then we can say, let's choose a subsequence length, m. So in this particular case, we're choosing the subsequence with length m equals to 4, right? Now that we understand what m is, how do we compare subsequences? Let's say, how do I compare this green subsequence with, let's say, this one over here on the right, shown in blue? How might we compare them? So to do this, one of the most intuitive and simple approaches to compare them is to compute something called a Euclidean distance. And the definition of a Euclidean distance is the straight line distance between 2 points. So what does this mean? So let's take these, let's simplify this a little bit. Maybe instead of taking 4 points, let's look at something that is a subsequence length of 2. So if I simply plotted these 2 points, 0, 1 is down here in the bottom left, and 1, 2 is in the upper right. These are just 2 points. And we said that in the definition that the Euclidean distance is simply the straight line distance between these 2 points. Now, let's not call it some fancy name. Let's just give it a letter h to represent it. If I want to calculate the straight line distance between them, we all sort of know how to do this intuitively with very basic math. So we can draw a triangle, and we know that if we have a right angle triangle, we can compute h by seeing that h squared is equal to a squared plus b squared. We take the square root of both sides, and now we have the Euclidean distance. And this isn't anything fancy. I'm sure everybody recognizes this, masquerading as everybody's favorite Pythagorean theorem. So it's pretty straightforward. Now we sort of intuitively understand how might we compare these subsequences. And so we can plug in our numbers, and we find that the distance between these 2 short subsequences is root 2. Now let's kick it up a notch, and let's increase the length of our subsequence. So notice here that we have added 2 new points to our subsequence, so it's of length 3. And now we modify our Pythagorean theorem by just adding the c-squared term. That's all there is. And we plug in our numbers in very much the same way with an extra term at the end in our summation. And we find that our distance, or the Euclidean distance between these 2 subsequences, is just simply root 3. And now if I add a 4th term here, which gets us back to where we started in the first place, we see that we have a d squared term, and we can quickly compute that the Euclidean distance between these 2 subsequences is square root 67. So not too hard. So obviously, as you add more terms or elements to your subsequence, there are more terms in your summation. Okay. So I'll pause. Ollie, were there any questions in the chat?
No questions right now.
Awesome. But if you do have any questions, feel free to throw them in the chat.
Okay.
Thank you.
Thank you.
So now that we've defined how we compare 2 subsequences, we might want to then think about how do we compute something called pairwise Euclidean distances. So not only do I want to compare 2 of them, but let's say I wanted to repeat my time series down here in the bottom, and I want to take this reference subsequence and I want to compare it to the entire time series down here, maybe through some sliding window. And I'll record the distances in this vector down here. And this vector down here is just known as the distance profile. So if we simply say, I want to compare this green rectangle with this blue rectangle, I know how to compute it using the Euclidean distance. And because they're the same, the distance is 0. That's pretty obvious. Now I can slide this blue box over by 1, compute the distance again, slide it over, compute the distance, and just kind of keep going all the way across. And basically, I'm comparing the green box to the blue box. And then eventually, I run out of subsequences to compute, and we get our distance profile. And this is what I mean by pairwise Euclidean distances. Now, once I do this, I can start examining this distance profile and asking, is there anything interesting here? So the first thing you can do is say, well, which subsequence along this time series is most similar to this green box? Now, the most obvious one is obviously what is called the trivial match or the self match. Obviously, you can match yourself. So this isn't particularly interesting. So usually we'll blank this one out, and then what we'll do is we'll scan across the remainder of the time series, or sorry, remainder of the distance profile, and look for the next smallest distance, which happens to be over here. So the closest match to this green subsequence is this blue one here, and they are separated by a Euclidean distance of 6.9. So we can continue this further. So this is just sort of one set of pairwise Euclidean distances. So what we do next is we can now take our reference window, this green box, slide it over by a single element, and we can just basically perform the same thing. Let's compute the Euclidean distance between this green box and this blue box. And we keep on sliding it across, computing every single pairwise distance, right? And really get a sense of how each of these subsequences match up. And again, we can find the closest one to this green one, and that's all the way down here, right? And it actually has a distance of 1.4. And you can see that these two sequences or subsequences are pretty close together. Now we'll repeat this, obviously, by moving our green box over. And as you can see, we could just keep doing this ad nauseum until our green reference box ends. And we end up with many, many different distance profiles. And if we start stacking these distance profiles, one on top of each other, we get something called the distance matrix, which is shown here. So each row here corresponds to one of those vectors that we had seen earlier, right? And all of these green boxes just denote the distance to its nearest neighbor for a given subsequence. Now, if you think about this distance matrix, right? All of this stuff seems pretty intuitive. We know how to compare our time series sort of with respect to itself, or perhaps with respect to another time series. And it's, again, very easy to interpret the meaning, right? We don't have to think about, well, what does a Euclidean distance mean? It's pretty straightforward. It's just a straight line distance. And we really haven't made any assumptions in the sense that this is generally applicable to any time series. It's not specific to, let's say, finance or any other particular area. And thinking about something that's parameter-free, realistically, we haven't really chosen any parameters. Maybe you could argue that the subsequence length, m, is a parameter, but that's just one parameter. And again, the great thing is that we don't have to do any model training. So there's no real prior knowledge that's required here. And so it really, this approach of computing these sort of pairwise Euclidean distances really satisfy our need, right, of finding something simple and intuitive. And so the next question that we would ask is the solution, is this particular solution scalable? Okay, because if we're thinking about a simple toy data set, maybe it works well, but does it scale to larger and larger data sets? So if we think about how we might build up this entire distance matrix, the brute force calculation actually can be done in a few lines of Python code. So in the top here, I'll draw your attention is n equals 13 is just simply the length of our time series. M equals 14 is just the subsequence length that we chose. And this is our time series that we were showing before of 13 data points. But really, to actually now compute the pairwise Euclidean distances for this distance matrix, it's embodied in 3 for loops. This outer first for loop controls the green subsequence that slides across. This J for loop controls the blue subsequence sliding across our time series. And then our innermost for loop here, K, actually computes the pairwise Euclidean distance for each of the elements within a given subsequence. So we have a triply nested for loop. And for those of you who are savvy with this type of stuff, this actually gives you a computational complexity of O of n squared by m. And also, if we were to sort of store this entire matrix, this distance matrix in memory, it would require a space complexity of O of n squared, which is typically not what you want to do. And to really drive home the point here, why don't we take an example of a brute force calculation of something, of every time series that's actually larger. So there's sort of a back of the envelope calculation here. So imagine you had some sort of IoT device where maybe you're collecting data every 3 seconds. So that means that you're collecting data 20 times per minute, and maybe you're doing this 60 minutes an hour, 24 hours a day, 365 days a year for 5 years. So that means that for 5 years straight, you're collecting data every 3 seconds from some sensor. This would actually produce just over 50 million data points in your data set. And if you were to take this brute force approach and to compute this distance matrix, all these pairwise Euclidean distances, it would actually take you just over 4.4 years to compute. And not even to mention that the memory requirements is 11.1 petabytes of memory just to store that into memory. So if we go back and ask the question, is this solution scalable? Unfortunately not. But at the same time, we now understand why. Even though there's a very obvious and straightforward and intuitive approach to analyze your time series data, since it wasn't scalable, that explains why these methods that you're seeing on screen here have become so popular, right? Because they do work and scale well to large data sets. Well, that is until now. So as I mentioned at the very, very beginning of this talk, a group of researchers at the University of California, Riverside and University of New Mexico actually published a series of back-to-back papers at around sort of November, December of 2016. And this paper outlines something called a matrix profile. And so when I saw this, it seemed quite interesting. It was related to these distance matrices. So what is a matrix profile? So the definition of a matrix profile is a vector that stores the distance between each subsequence within a time series and its nearest neighbor. So given, let's say, one of those green subsequences, you're only storing the distance to its nearest neighbor. So conceptually, what this means is that given the distance matrix on the left here, all we're doing is taking those green boxes, which denotes the distance to its nearest neighbor for a given subsequence, and we pull them out. And we store only this information in a single vector. So this means that instead of storing the full n squared distance matrix, we just simply store a vector that is of length n. And now these researchers then went on to also claim that not only is it sufficient to just store this matrix profile, but that they could actually do this exactly in O of n squared computational complexity time, right? And that sounds sometimes too good to be true. But let's just set that aside. So given this matrix profile, let's say for this particular time series, this is the matrix profile for it. What can we do with this matrix profile? So the first thing you can do is you can plot it and use it to annotate your original time series. So we'll plot that here. And so when we look at it, we'll observe a couple of things. We'll see that it sort of goes down and then back up, right? And then down again. So we see some minima over here, maybe potentially some maxima over here. Now, if we actually explore those global minima, there's 2 of them, right? These 2 right here with a distance of 1.4. And we're aligning our matrix profile with our original time series. So these distances actually correspond to the one on the left corresponds to this subsequence, and the one on the right corresponds to this subsequence. And it just so happens that this is often called, this global minima is called a motif. So these 2 subsequences happen to be very, very close to each other. Because if you look at it, the very first point are the same. The second point are off by 1. The next point is the same. And the last point here, 9 and 10, are just off by 1. And so you understand conceptually why these are perhaps a good match. And this is a potential pattern within your time series. So whenever you have a motif, that is an opportunity to identify something as a pattern. Now we can take this a step further, right? And or the researchers took this a step further and said, not only should you be aware of something called the matrix profile, but there's something also called the matrix profile index. So the index, which is the index location of the nearest neighbor for a given subsequence. So going back to our example here, the subsequence on the left has a nearest neighbor that is a distance of 1.4 away from it. And it just so happens that that nearest neighbor, the subsequence of it, starts at index 8. So this is 8 here. All we got to do is come up here and find index 8 and find that this subsequence is this one's nearest neighbor. Similarly, this one over here, this blue one, also its nearest neighbor is at index 1, and so it's pointing up here. Now, just to drive home this point here, if I and obviously every other subsequence within this time series also has a nearest neighbor. To further interpret this, what if I took, let's say, this subsequence over here? To find out where its nearest neighbor is, we just come down to our matrix profile, which is aligned with our time series. And we see that it's this green subsequence's nearest neighbor starts at index 2 and with the same length. And so we just come up here to index 2, and we find that this is its nearest neighbor. And these two subsequences simply have a distance of 6.2. So we can quickly interpret what the meaning of this matrix profile is very quickly. Now we can do something else. So instead of looking at global minima, we can also look at the maxima. So if we scan across our matrix profile, we see that the largest value is 14.1, and this corresponds to this particular subsequence. And what this is telling you is that this particular subsequence doesn't actually have any other subsequence that looks like it. In fact, it looks so different from it that it has a distance of 14.1. And so what this is suggesting is that this subsequence is a potential discord, or it is a discord, but that it is also a potential anomaly within your time series. So think about this. If you're able to compute your matrix profile, you essentially get patterns searching or pattern matching for free, as well as potential anomalies for free. Now, we talked about the fact that the brute force method had a pretty nasty computational complexity as well as space complexity. And these researchers at the various institutes published a series of papers. In the first paper, the algorithm was called STAMP, which leveraged a fast Fourier transform to shave off some of that computational complexity, so it became O of n squared log n. They then published another paper where they introduced an algorithm called STUMP that does the same calculation, but instead of computing this full matrix profile in n squared log n, it does it in n squared time. And then this was performed on CPUs. Then they thought about, well, what if we throw better hardware at it? And so they produced something called GPU stomp. So they migrated this stomp code over and applied it onto GPUs and found basically that it could be really, really fast. And in fact, in their published work, they demonstrated that they could compute for a time series of length 100 million, right? Which is twice the amount that we had shown for that brute force calculation. They could use their implementation called GPU Stomp, which is using 2 GPUs, and they could compute the full matrix profile in just over 12 days. All right. And if you think about this is basically like taking 10 years worth of data, right, and computing this in 12 days, which is faster than real time, so to speak. And if you were to do this in the brute force way, you'll see that it takes about actually 1,600 years to compute. So you don't want to be doing this the brute force way. And even this is Eamon Keogh. He is one of the primary investigators of this matrix profile work, and he said that given the matrix profile, most time series data mining problems are trivial or easy to solve in a few lines of code. And he also later went on to say that these are the best ideas in time series data mining in the last 2 decades. And in my opinion, anybody who says this has to be a real gangster. But being a scientist myself, I like to think that extraordinary claims require extraordinary evidence. And this was stated by the late Carl Sagan. And so this is where our journey at TD Ameritrade started, which is we decided to, from this published work, we thought, how could we actually try validating some of these claims of being able to not only compute the matrix profile, but to be able to do it in a short period of time. And so based on their published papers, we tried implementing it. So we tried validating it. So we used Core Python, and for the numerical computing components, we tried NumPy. And the first thing that we did was, so we actually didn't look at the full 100 million length time series. We just took something pretty modest. So this is about 2 million data points in length. And in their published work, using their GPU Stomp algorithm, they demonstrated that they could compute the matrix profile in 9 minutes. So I implemented the same thing. right? And on a single CPU, it just took way too long. It doesn't even register. It was more than 300 minutes. It was way, way too long. And this made me a sad panda. But then I started thinking about, well, what if we tried to parallelize the code? Maybe using multiple CPUs, not just using a single core. Well, then I started looking at using something called Numba. So Numba is open source software that is really a great tool. So for those of you who are maybe more familiar with using things like Python, Numba basically allows you to write Python code, and it JIT compiles that code for you. And not only does it do that, but it also automatically parallelizes that code for all of the CPUs that are on your particular server. And so we applied Numba to 16 CPUs, and we were able to see that we were able to actually compute this matrix profile for 2 million elements in about 3 hours. But something to note here, right, is that we moved from a single CPU to 16 CPUs in 2 days. So I know a lot of people like to give Python a hard time, but we think about this. We were able to move to multi-CPUs in a very, very short period of time. So if you're interested in parallelizing your code, I would highly recommend using Numba. Then we thought, well, what else can we do? If we think about the algorithms that were published and think about the brute force method, there's really a space that we realized was missing from just looking at a single or parallelized CPU code from looking at GPU code, and something in the middle, which is what about thinking about multi-core distributed, right? And that's when we decided that we were going to leverage the right tool for the right job. In this particular case, we looked at Dask, and specifically Dask distributed, where we can distribute our code across multiple servers now, and then parallelize across each individual server. And now we were then able to scale up to 128 CPUs, right? And that brought our computational time down to 13 minutes. And remember this, we started with pure Python or NumPy code, and we were able to now distribute across 128 CPUs in a matter of 7 days. Within a week, we went from single CPU to distributed multi-core CPUs, which is a testament to the development of these open source tools and why we need more of them and why you should use them as well. And so now that we know that we can distribute it that now we understand it's scalable, we sort of went back to the original publication that looked at a time series that was 100 million data points long. And if you recall, this GPU Stomp, it was able to compute this in just 12 days. And now using our implementation, now with 256 CPUs, we were actually able to compute this matrix profile in just under 10 days. And now, just to be clear, we're not saying that CPUs are faster than GPUs, because that would not be a smart thing to say. But what we're saying is that Python code on CPUs is actually quite scalable. So you can get there very, very quickly. When we scaled to 256 CPUs, we didn't actually have to change your code. We just had to spin up our extra servers and then run the code, and it was essentially complete. So going back to our original question, is the solution scalable in terms of computing this matrix profile? Absolutely scalable. So we can now start thinking about how to analyze our data. Our version of this algorithm, this sort of distributed parallelized version of our algorithm, we call it STUMP. So it's kind of a play on words of the published algorithms of STAMP and STOMP. The U sort of pays homage to the fact that we're using Numba and NumPy sort of in the numerical computing world, but also because Ann Arbor, Michigan is often known as sort of tree town or tree city United States, and so we aptly named our algorithm STUMP. Now you might also notice that we have stumped with an ED at the end. If you're looking to use that algorithm, that is actually our distributed algorithm. So STUMP is for sort of on a single server. Stumped is for multi-server computation. So you can compute your matrix profile on a single server or multiple servers. And just so we can kind of visually see what that performance looks like, here is this benchmark. So this is this GPU Stomp, this published work, right? These are some of the few data points that they demonstrated. And again, this is using 2 GPUs. And what I'm going to lay on top of this is our CPU. So this dotted line up front here is using 2 CPUs, 16 for this one. And this line out here is using 128 CPUs. And you can even see here, this 256 CPUs is doing nearly as well as the GPU version. So it scales out pretty nicely. And so now we're at May of 2019, so just about a year ago, where we sort of wrapped up this work, and we decided at TD Ameritrade that we were going to open source this and share this with the data science world and share this with the public as part of our effort to transform lives for the better. And this is where STUMPY comes into play. So STUMPY is a powerful and scalable Python library that efficiently computes this matrix profile. And once you have this matrix profile, you can use this for a variety of time series data mining tasks. And we'll get into more of that in our live demo later. When we first released this last year as a version 1.0, we had full unit test suite with 100% code coverage and minimal dependencies. Oftentimes you get these data science packages that are very dependency heavy. We only rely on NumPy, SciPy, and Numba. And then if you want to do the distributed version, then there's a soft dependency on DAS. But it is compatible with Python 3.6, and you can conda install it through the conda forge channel, as well as pip install. And obviously, you can find our code on GitHub. Here's a short version of the URL at tiny.cc/stumpy-code. So go check it out there. I'll post this at the end of our talk as well. And then with that, I'll pause for questions before we get to the second part of our talk, which is the live demos, the most fun part. Ollie, were there any questions?
We just had a question come in from Paul. What can you do with the resulting computation? How is this information visualized?
Perfect. I think we'll hold that question because we're right about to get into the live demo. How about that?
All right, let's just jump right in.
Okay, so just maybe to keep you a little bit more suspense, just a quick year in review. So again, STUMPY was released in May of 2019, and we're now in July of 2020. And so obviously we celebrated our STUMPY's first birthday, which we're pretty excited about. And since that time, we've had tremendous growth, around 36,000 downloads and installs, and constantly increasing. We have a ton of great documentation and tutorials, which I'll outline, which I'll show and point you to later. But just to kind of show you that people are looking at our documentation throughout the day, and not only that, but also throughout the entire world, whether it's in India, Australia, even folks in South Africa are really using STUMPY and reading our documentation. And also, we have just over 1,300 GitHub stars. So thank you to all of the people who gave us a star. And now we're at version 1.4.0 since our humble beginnings of version 1. And there were some things that a lot of new features that we've added since then. The first and most important thing is sort of what I call sort of the need for speed. We obviously did a lot of CPU work, but we also thought that, well, what are our friends that are not that are doing deep learning? What should they be doing when their GPUs are idle? Well, we thought, well, could we take this, STUMPY code and port it over to GPUs? And maybe how might we create something called GPU stump? Right? Obviously, the published work did something like this. Could we follow in their footsteps? But in order to do this, we had to think about, well, how do we incorporate and sort of access GPUs? For those that are doing deep learning, you're probably familiar with PyTorch coming out of Facebook, or even TensorFlow from Google. A lot of these APIs for doing deep learning or computing on GPUs tend to be changing very rapidly. There's also a new kid on the block called QP or QPy, which is meant to be a drop-in replacement for NumPy. So check it out if that's your cup of tea. Or some people actually write raw CUDA kernels or raw CUDA code and then wrap it in Python, right? But a lot of times with sort of these packages constantly evolving, right? It's somewhat hard to keep up. But as a maintainer of STUMPY, one of the things that I really wanted to try to avoid was any additional dependencies. We really appreciate the fact that you can, as a user, download and install STUMPY. Hopefully, within 30 seconds of doing that, you can run and analyze your data. But if there were additional dependencies, this becomes harder. And I kind of think about it as you're drawn into dependency hell. And so it turned out that really the right tool for the right job wasn't any of the packages that I talked about earlier, but instead, the right tool for the right job was Numba. So not only does Numba allow you to parallelize your code, but Numba also has GPU support and allows you to CUDA so it allows you to JIT compile your code directly to CUDA code, which is phenomenal. Now, obviously, there's got to be a catch, right? So what's the catch? So there's a couple of pros and cons for those of you who want to do this type of work. The really great thing is that, again, no additional dependencies, which is a plus, right, if you're already using Numba. But you do have to maintain a separate code base that targets a GPU. So you can't just take your straight Python Numba code and then say, put it on GPUs. You still have to write it differently. But the good thing is that you're still writing Python code, which I love. Now, having said that, there is, and this isn't necessarily a Numba problem. This is more of a GPU issue, which is you have to think about multi-threading, this multi-threading paradigm in GPUs, which is fundamentally different from the way that you would code for CPUs. But once you sort of wrap your head around that, then everything becomes smooth sailing. And another great thing is that you write Python code and it automatically compiles to CUDA. So you don't actually have to keep CUDA code with your package. All of that's handled for you, and you don't have to compile any of it or stuff it into your Python packages. Now, there is one con, which is if you're using Numba, you might have a delay in the CUDA functionality. So if new CUDA functionality comes out, it might not immediately get added to Numba quickly. But Numba also has excellent host-to-device APIs for moving data from your host, which is your CPU side, to your device, which is your GPUs. But to also keep in mind that with using GPUs, there could be memory limitations. So a lot of times if you're using commodity GPUs, you might be limited to, let's say, 11 to 12 gigs of GPU memory. So you should keep that in mind. But again, out of the box, using Numba, you can actually leverage multiple GPUs if you have multiple GPUs on the same server. And then last but not least, this is probably the most challenging bit if you're open sourcing your packages, is writing unit tests for Numba GPU code, and then also continuous integration for GPU code is quite complex, especially when you have a package like Stumpy that tries to maintain 100% code coverage. But we can discuss that maybe in the Q&A if you're interested. So taking a look, obviously we were able to successfully do this and port our code over to GPU, and we created something called GPU Stump. And this is, again, the CPU is shown in purple. The yellow is really that published benchmark. And what I'm going to show you in blue here is the dotted blue, the dashed blue line is our GPU Stump analysis, or creating our matrix profile using a single GPU. Right, which isn't bad at all. And then with 2 GPUs, it basically performs nearly as well as the benchmark. And thanks to our friends over at NVIDIA, shout out to Ben Zaitlin, as well as Josh Patterson over there, we actually ran Stumpy on their DGX1 and DGX2 GPU cluster, which has 8 and 16 GPUs on the same server. And you can see that Stumpy actually scales out almost linearly, all the way out to just over 130 million data points. And mind you, we didn't have to change a single line of code. We just installed the Stumpy code onto that server, and we just ran it without any issues. So it really is a testament to how great the software Numba is. So now that we've shown this, I'm sure everybody's thinking, well, in order to run it on GPUs, it must be a bit of a change in the code. Turns out, this is what it looks like. So imagine you have a time series that looks like this. This is just a simple example using 10,000 data points. Then your subsequence length is 50. The CPU version of the code just looks like this. You just call Stumpy stump, or the stump function, and then you hand it the time series as well as the subsequence length. And if you wanted to do this on GPUs, this is the GPU code. Notice here that the difference between the CPU code and the GPU code, assuming you have a GPU on that server, is just 4 characters. So you don't really have to change much. You can test it on the CPU and then move it over to GPU without much hassle at all. I'm sure that a lot of you are thinking, can I have a GPU as well? I'm on your side, and it turns out that you can have a GPU as well. So there's something called a Colab. So for those who aren't so familiar, the Google Colab in my brain is sort of Google Drive meets Jupyter Notebook. So this is Google Colab is from Google, and so there's a link down here. So if you go to tiny.cc stumpy_colab, right, you'll be able to access this example Stumpy notebook that actually walks you through how you might run Stumpy on GPU. And actually, Google Colab offers you a GPU to use for, I think, for 12 hours, if I'm not mistaken. So go check out this this notebook. And again, I'll post this slide at the end here, or this link at the end. So now that we have GPU Stump, so we've scaled across to GPU devices, we've also added something called M-Stump. So the M standing for multi-dimensional stump. So the multi-dimensional component of this is if you have multi-dimensional time series. So then maybe instead of having a single, let's say, sensor collecting data, you might have 10, 20 sensors collecting data at the same time. Maybe you're collecting temperature, pressure, and so on and so forth. You can actually analyze all of these time series together as one. And so there's also a distributed version called M-Stump. Also, we have an approximate version of the code called Scrum. So where you can compute an approximate matrix profile without committing a full large amount of time computing the full thing. You can actually get a pretty good approximation of it using this algorithm. And if you're looking for streaming data support, we also have that too now in Stumpy. And so I'm going to move into the live demos, and I'll switch over to our browser over here. So this is our code on GitHub. So check us out, or you can just search for Stumpy Python. Here's the notebook, the Google Colab that I just mentioned. So in just a few lines of code, you have access. It shows you how to install Stumpy on that Google Colab notebook, how to import the package, and then finally how to execute the Stumpy code on CPU and then also on GPUs, and in a few short lines of code. But here's really where the fun begins. So here is an example. So I want to draw everybody's attention to the very top here. So this is a time series at the very top, right? I want everybody to take a look. Can you spot anything interesting coming from this time series? Are there any repeating patterns? Maybe there is, maybe there isn't. Can you spot any outliers, any anomalies, right, in this time series? Now, not to belabor the point here, but even what if I showed you that this is actually the pattern that you're looking for? Again, hindsight is 20/20. So your data, with your original data, you won't know this, obviously. But what if I showed you this pattern, and I've zoomed in green here? So I've blown it up, and you can see it in green. Can you spot where along this time series does this pattern repeat itself? And it turns out what matches this particular time series, or what matches this particular pattern, exists all the way in gray on the other side. And I've also overlaid this gray line on top of it. And you can sort of see exactly why this gray subsequence matches the green subsequence. And this number here, this 5.5, is that Euclidean distance that we talked about. So it's not 0, because there are some differences between these two subsequences. And those differences can be attributed maybe to this section over here and a little bit over here. But for all intents and purposes, you probably agree that these two subsequences are a match towards each other. And what we're showing you here is that matrix profile, right, for every single sliding window of this green subsequence that moves across. So you can see that the global minima is located right over here and right over here. So where the green and the gray boxes sort of are aligned right on top of it. And now that explains that the global minima actually give you that motif and give you a very strong pattern match. But because we have all of the pairwise distances, when I press play here, it will basically slide that green subsequence, this sort of reference window, from left to right, and you'll see this gray box jump, right? Because it actually spots where that closest pattern is. So I'll play that for you, and you'll see, right? Now, one thing to point out too is that wherever your reference window is, this green box, what matches that pattern doesn't always have to occur in the future. It can also occur in the past as well. So that's why you see this gray box behind it. Right? So there's something to keep in mind. And going back to what we were saying about looking for potential anomalies. So to do that, you basically go to your time series, your matrix profile, and you look for the maxima. In this particular case, that's this green subsequence right here. And you can actually see that the closest match to this green subsequence is this gray subsequence. And it actually has a distance of about 22.3, which is a very, very far distance away. You can tell why, right? They're not actually that great of a match. There's huge differences over here and differences all the way over here as well. So just by computing the matrix profile, all you need to do is just look at your, all you need to do is just look at this matrix profile, look for the minima, and you might have multiple minima or local minima along the way. And you can also analyze the maxima as well. Now, there are a couple of other things that you can do with this matrix profile. I recommend everybody go to the STUMPY Read the Docs documentation. In our tutorials, we have wonderful, very full-length tutorials, very verbose, that actually tries to take the original publications and reproduces a lot of the figures from those papers and elaborates on some of those concepts. But a couple of things that I think are quite exciting, that once you compute that matrix profile, what can you do with it in addition? So one of these things is you can look at something called time series chains. And what is a time series chain? So if you can imagine this plot here where each data point might be a subsequence, right? And if you have points that are close together, it just signifies that you have subsequences that are close together, in Euclidean distance. Now you could have subsequences that are just clustered randomly but very close to each other. But you can also have subsequences that are close to each other, but that that are different along some sort of directionality, along some direction. And here's what I mean by this. So if we kind of scroll down here and we look at this particular time series. So this time series is search queries for the Kohl's department store, shopping store. And this is just showing you how many, I think, Google web searches that people have been querying since 2004. So we see, year over year, right? Obviously, there's an upward trend. But also what we're noticing is this little hump here, sort of near the end of the year. And maybe I'll have you kind of do a little thought experiment of what does that hump represent? And the point here is that if you take this time series, this raw time series, and compute the matrix profile, what you can extract out of this are the minima, which are your motifs. But then you can actually take this matrix profile and compute the time series chains. And what it will do is it will highlight for you from this time series a pattern that's not only repeats itself over time, but that is sort of monotonically moving in a certain direction. So you can see that the time series chains computed from the matrix profile, right, has extracted these particular humps along the way. Again, somewhere near the November and December timeframe. And there's two things to note here, right? In this particular pattern in 2004, it was just one straight hump. And then in 2005, you start to see what looks like this sort of bimodal hump. And then over time, we see that this first peak actually gets larger and larger and larger. And it turns out when you analyze what's happening or what date these peaks are occurring at, it turns out that this sort of solid blue line is happening right around Thanksgiving. And this dotted or dashed line is happening in Christmas, during the Christmas holidays. So as you can imagine, this first peak refers to Black Friday, okay? And then the second peak refers to Christmas holidays, people just buying, maybe in Boxing Day in Canada, let's say, right? But what's really interesting here is that this time series chains is able to not only find a pattern that repeats, but that is changing across time, but it's also seeing that this first hump is increasing as well. And this is because in around 2007 or 2008 is roughly when the phrase like Black Friday came to be. And so you see this huge spike due to further purchases or search of maybe deals during that period of time. Another really interesting thing to look at is once you've computed the matrix profile is something called semantic segmentation. This is perhaps closely related to what our previous speakers talked about in terms of change point analysis. So in this particular plot here, we're actually monitoring a blood pressure of a patient who is actually lying vertically on a bed. Initially lying flat on a bed, and then all of a sudden that patient's bed is sort of tilted vertically, and this is where you see the blood pressure suddenly change, right? And so the question is, can you find an automated way to actually assign these changes, where the change point is, or whatnot, right? And this actually with matrix profiles, you can actually compute this for free. So as you can see here, there are these patterns that happen when the bed is flat, and then can we actually identify where we might place this dotted line to separate these two regimes, and you can do that out of the box with STUMPY. So going back to maybe to wrap up on this presentation. Obviously, you can do many different things, whether it's motif discovery, discord detection. We talked about doing multidimensional, computing multidimensional matrix profiles. We also demonstrated about time series change, semantic segmentation. But you can even perform clustering. You can also do shapelets and something called snippets. You can read up on that or ask me for more details. And just a lot more things you can do. And check out the GPU version as well. A couple of calls to action. The first thing is that we'd love for people to contribute to STUMPY, whether it is contribute PRs, even documentation adjustments or corrections is greatly appreciated. Please communicate. Tell us what you're using STUMPY for, and tell all of your friends about STUMPY. And the last thing is, nothing makes me happier than if you consider using STUMPY, so consume. With that, again, if you're looking for STUMPY, plug it into your favorite search engine, look for Python STUMPY. All the tutorials that you were just looking at, you can find at tiny.cc STUMPY tutorials. The live demo that you can play around with can be found at tiny.cc STUMPY demo. And then you can also get to that collab notebook at tiny.cc STUMPY collab, as well as the GitHub code can be found at tiny.cc STUMPY code. And then obviously the docs at STUMPY docs. And with that, I'll take any questions. And thank you so much for your time.
Thanks so much, Sean. Can we please give Sean a round of applause in the chat? All right, let me just paste mine in there. So while we are waiting for questions to come in, I did have a couple of things. Like, this is an open source project. You are managing it. Like, being like a data scientist turned developer, what are like some of the lessons you've learned creating this library?
That it will consume all of your time. I think that's sort of it's kind of like sometimes a thankless job. Although luckily a lot of our users are very appreciative of the time that we spend on it, and I try to take it very seriously. But I think it's if you want something to be quote unquote successful, I think that not only do you have to put the time and effort into it, but you also have to spend a lot of time spending time on the marketing side. Right, so getting out there, getting the word out, giving presentations and meetup groups, I think is a great opportunity. Attending conferences, right? But that does take up a good amount of my time as well. So,
do you have stickers?
We actually do. So we'll have to send some over to you.
Yeah, that'd be great. We can definitely pass them around next time we start meeting in person. Also, I'm not too sure if you're able to talk about this, but we had a question if STUMPY has really revealed any insights for TD Ameritrade.
So I'm not at liberty to talk about that, but I can actually at least tell you about some applications. So we've certainly seen a lot of interest in people leveraging STUMPY, especially in the finance world, looking at trading and stock ticker prices. We actually have somebody at CERN who's leveraging STUMPY, so at the Large Hadron Collider, looking at using STUMPY to tune sort of the acceleration of these lead ion particles, and then and stabilizing them, right, and understanding how that might work based upon the time series. Also, we have folks over at Dell who are leveraging STUMPY to analyze call data, so customer call data, which I think is fascinating.
Yeah, it's great, like how the work you've been doing at TD can like affect so many different people. It's like the power of open source. Like, what got you so into open source and like you wanting to create a package that you can release out to the world?
I think it was initially seeing how welcoming the open source community is. Again, being a former academic myself, you always we're looking for things that were for free, right? And oftentimes that open source community has already done a lot of that legwork for you, right? So we have packages like NumPy, SciPy, Dask, Numba to think, and this is sort of one way that we're trying to give back to that community, and hopefully at least we understand how hard it might be to take something that's from the academic world and produce it and package it in a way that is easy for anybody to use, right? So hopefully, if you're using Stumpy, whether you're a scientist or a developer, hopefully it's easy. And if it's not, please let us know.
So it's like, are you trying to make like a Pythonic type of API? Was that like one of the goals?
Yeah, not to give the academic researchers a hard time, right? But even their code, when technically their code is open source, they're very much for reproducibility. But their code was either in C++ or in MATLAB code. And really, what I did was I took it out of the confines of the handcuffs of that environment and brought it to where the data scientists are, right? Which is really in Python. And oftentimes, I think I actually did a poll on Twitter to ask, like, as a engineer, as a data scientist, if you're trying to analyze some data quickly and a package says that it is able to do this, how likely are you to download the code, clone the repo, and install it, compile it, and so on and so forth? And it was basically, I think it was around 75 to 80% of people said no thanks, right? Right. So this kind of speaks to what we're trying to achieve here, right? Is move quickly.
Yeah, like one of my previous jobs, like we were helping data scientists package up their like models and run them on like an Airflow type of system. And a lot of the work I had to do was just like getting the dependencies working. It's like I was building all the Docker containers and just getting that up and running. It's a headache all in itself.
Yeah, not everybody has that. It has the ability to, let's say, spin up Docker and deal with Docker containers, right? And really, we're just trying to make this dead simple.
Yeah, awesome. Also, we did have one more question. I think I'm going to butcher this name. So you mentioned Iman Keog. Do you have any other search terms for finding other applications?
Sorry, other search terms? Oh, for other applications?
Yeah.
Yeah, absolutely. Maybe I'll just show this from the...
Yeah, let me add that screen back.
So am I sharing right now still?
Yeah, you're sharing.
Okay, awesome. So if you actually Google UCR matrix profile, right, you'll get to Iman's research page, and sort of tucked in down in the bottom here. I mean, I strongly recommend everybody, if you're really interested, check out all these papers. They have around like 20 papers that are published. They're all fascinating, right? But just know that what we've done in Stumpy is implement exactly what is in these papers, right? So that you don't have to. You don't have to reinvent the wheel. But in terms of applications, they have this wonderful PDF down here, which says 100 time series data mining questions with answers. So I recommend you checking out this particular paper because it basically steps you through like all of the different potential applications, which I think is fascinating. I think they're continually adding more and more applications, right? So I strongly recommend it. There's a lot of really fascinating things here. So
that's really cool. Yeah, I'm definitely going to be pasting that link in the chat for later for those folks who need it. I actually did want to ask about your 100% test coverage. So like, so it's like, like, how are you testing Stumpy? Is it like sort of just like computing these profiles for a known matrix or for like a known series?
Yeah, that's a great question. Obviously with the code coverage and unit testing, take it with a grain of salt, right? It's more for my own satisfaction more than anything, right? So believe what you will about what that number means. But setting that aside, with the way that we're testing Stumpy, I think is quite unique. So the first thing that we do is we obviously have something that's very deterministic. So we have known inputs and known outputs. And really what's interesting here is that we showed the brute force way to compute a matrix profile. So we actually have a naive implementation that we can compare against. So that's actually what we do. So we take a known deterministic input, we compute it using these fast algorithms, and we compare it against the naive output. But what we also do is every time we're running that code, not only do we have a deterministic input, but we also purposely allow for a non-deterministic or a stochastic input. So we actually have a random sampling of a input time series, and we've actually found errors, right, or bugs when we first started, thanks to this approach. So we sort of have a two-pronged approach. And so for every single fast algorithm, we actually have its counterpart, which is what we call the naive algorithm. And so we have a Python module called naive.py in STUMPY, so people can actually see what is actually happening if you break it down.
That's very interesting. I'm really fascinated by this like testing methodology. Have you considered using something like hypothesis to do like property-based testing?
We for a hot second we thought about using hypothesis, but I mean, mind you, we're maybe taking next steps. We're not even at the stage of looking at things like integration testing and so on and so forth, right? But with hypothesis testing, I think what tends to happen with hypothesis testing is that you're analyzing sort of individual points, right? Maybe it's a single integer or a floating point or a Boolean, right? In this particular case, our data is just a sequence, right, of floating points. And so there's not really much there. We do have, even in STUMPY, we do have NaN and inf and support within your time series. So that's all possible too. So you can have missing data, so to speak, within your data, and it works perfectly fine. So that's all tested within our work. I mean, if you decide to pass a time series with string characters, that's probably beyond the scope.
Yeah. I guess that should be producing an error in some sort of instance.
Yeah.
So you did mention different ways people can get started contributing. Is there anything that you're looking for in particular?
I think documentation, is the greatest thing. So considering that in STUMPY, we actually try very hard to be inclusive, right? And all of our tutorials actually reproduce some of this all of this academic work that I showed you back here. Right, all of these, some figure in one of these papers, and oftentimes it'd be very helpful if somebody wants to contribute, the reproduction of one of these works, or just to engage with us in our GitHub issues. We try to be exceptionally transparent. We try not to hide behind some hidden like Slack channel, let's say. So everything is out in the open. All our conversations are on our GitHub issues. Feel free to post anything up there, ask us questions, and contribute what you think will help make us better.
That sounds fantastic. For contributors, is it mostly folks from TD Ameritrade? Have other companies started making contributions?
Yeah, we've had a handful of folks. In fact, some of our earlier contributions was somebody that was out in Sydney, Australia, that helped us get our continuous integration up and running. We got folks here at the University of Michigan that were helping out. Shout out to Bradley Dice. Also, you mentioned the folks over at CERN who are using it. They're definitely heavy contributors back to STUMPY. And so we're seeing a good amount. And even people, again, I think contributions even to improving documentation is really what is just as valuable as the core code.
Yeah, I think that was sort of the way I first got started. And it's like, it means so much because that's the first place people go for help. And if you have poor documentation or something that's not very clear and not reproducible, it adds just such a hard, like a barrier people can't cross. So yeah, definitely give a shout out to documentation. All that work is definitely underappreciated. So do you have anything else you would sort of just like to mention about STUMPY that we sort of have not covered?
No, I think that's about it. Again, get out there, use it, provide feedback. Always happy to hear back from users.
Awesome. And can we get another round of applause for Sean in the chat? But before we do let you go, is there a call to action besides going out and using STUMPY?
Yeah, just a reminder, PiData Global is coming up. So make sure that you get your proposal in for a talk by August 2nd.
Awesome. And I will also add that to our Slack channel. We have a call for proposals channel. So join that to get latest information for CFPs. I want to say thank you so much, Sean. This was a very fascinating presentation, and I definitely learned a lot.
Yeah, thanks so much, Ollie, and thank you, Chippy.
Yeah, we'll see you around.
See ya.